Today we're going to have a look at how to describe how a spirometer is used and calculate and interpret data. So you should have already seen the video on how to use a spirometer. Now what we're going to do is have a look in your notes at page 17 onwards, and you've got this picture here, which is a picture of a spirometer and a kymograph. A kymograph is just the device used to record the trace. Going to look at the different parts of the trace and how you can analyse the measurements given to work out things like tidal volume, which is your normal breathing rate, so that's the amount of air you breathe in or out in one breath, shown by this curve here. You've also got your expiratory reserve volume, which is basically the volume you expire. Please note that it's the one going upwards that's expiratory reserve volume, because this is a spirometer trace. Anything extra below the curve for your tidal volume is the inspiratory reserve volume, shown here, this gap here. You've also got the residual volume, which you'll notice the spirometer trace does not reach into, and that's because this is the volume of gas that you find in your lungs after a breath out. You cannot get rid of this volume of air, because if you did, it would cause your lungs to collapse. They'd be in a vacuum. Your total lung capacity, therefore, is the amount that you breathe in and out plus the residual volume. You've also got something called the forced vital capacity, which is the volume of air breathed in and out on a maximum forced breath. So you can see that that includes the expiratory reserve volume plus the inspiratory reserve volume and your normal tidal volume. And then the last one is your functional residual capacity, which is basically your residual volume plus your inspiratory reserve volume. So onto the spirometer then. On here we have a picture of a spirometer with the kymograph, showing that there is water in the chamber and air in the separate chamber. Basically, you attach yourself here to the mouthpiece. You have a soda lime to absorb any carbon dioxide that you're breathing into the machine. As you breathe out, air enters the machine and the pen goes upwards as the chamber moves upwards. As you then breathe in, you remove air from the chamber into your mouth. That causes the chamber to fall, and so you get a downward trace. So on a spirometer trace, the upwards trace is for you breathing out or expiration, and the downward part is inspiration. The volume will eventually go down, as you can see on this kymograph here. The volume is slowly going down. That's because as you take out oxygen and use it up in respiration, the volume of gases returned would be the same volume. However, some of those gases are contained here by the soda lime, which is the carbon dioxide. Therefore, the total volume that re-enters here is less than you took out. Therefore, over time, the total volume will go down. Okay, so this is basically a spirometer trace, and you can see the shape going downwards. And you can see that there is a triangle drawn on the part that's going downwards. That's helping you to calculate your oxygen consumption, which we'll come on to in a moment. You've also got a large upward stroke and a large downward stroke, showing you the you can work out the forced vital capacity if you measure peak to trough. So trough down here, peak up here. And this may be after exercise due to the number of breaths, but always notice on the trace the time given, which will be on the x-axis, and the volume, which will be on the y-axis. And then you can basically work out what each square value of each square is, and then use that information to calculate the size of your lungs, the size of your tidal volume, and the time taken to do any breathing. So again, here is your trace. This one is a lung volume trace, and we can tell that because the reserve volume at the top here is inspiratory. So the only time that the volume will increase is when your lungs are inspiring. So this must be a trace from a lung volume. So just watch out for that. Always look on the y-axis, whether it's the lung volume trace or whether it's the spirometer volume trace. If it's spirometer volume trace, then you expect the upward stroke, which is this bit, to be expiratory reserve volume, and this is expiration. And in a lung volume, then this is, as shown here, is inspiratory reserve volume, and this part is inspiration. Okay, so this is a spirometer trace taken from an electronic spirometer, and so as a result of that, it actually records your lung volume. So expiration in this case is the upwards trace, and inspiration is the downwards trace. So these are normal breaths for your tidal volume. So again, tidal volume is the total volume breathed in or out in one breath. So it's just the height of each of these peaks. So you would take 5 to 10, depending on how many you are given, and work out a mean average. Then over here you can see you've got the extra inspiratory reserve volume and expiratory reserve volume, giving you the forced vital capacity. So from trough to peak, which is the total volume of air breathed in and out in one maximum forced breath, gives you the forced vital capacity. You can see on the y-axis you've got lung volume, so you know straight away that if it's lung volume on this y-axis, upwards will be inspiration, downwards will be expiration, and time along the bottom in seconds. So this is one of the ones in your text, in your notes books, for you to try and calculate. All I want you to do is work out how much decimeters cubed you find in 1 square. So if 10 squares is 1 decimeter cubed, then 1 square will be 0.1 decimeter cubed. And then all you have to do is work out the height of each peak. And here you will see, if you count the number of squares and average, mean average, you get 4 squares, so it's 0.4 decimeters cubed. If you want to work out the breathing rate, on the other hand, what you have to do for that is you have to work out how many squares per second. So here we've got 5 squares, and each 5 squares is worth 4 seconds. So if you do the calculation, you can basically work out that each square is 0.8 seconds. Then all you have to do is find where the pattern repeats. So from here to here, we have 3 complete breaths. So we can say that we've got 3 complete breaths in, if you count those squares, you get 20 squares. So 20 squares is approximately 16 seconds. So 3 breaths every 16 seconds. Then what you need to do is work out how many breaths you'll get in 60 seconds. So 3 divided by 16 multiplied by 60 will give you 11.25 breaths per 60 seconds or per minute. And so there you have a breathing rate. You then use the tidal volume multiplied by the breathing rate, and that will allow you to calculate the next calculation in your notes, which is the pulmonary ventilation rate. So the pulmonary ventilation rate is there. So you get a value around 11 for your breathing rate from that graph, 0.4 for your tidal volume, and you multiply the two together. Forced vital capacity is nice and easy. You're just measuring the height. So again, you can see 1 decimeter cubed is the equivalent to 10 squares. So all you have to do in your notes is work out how many squares there are for the forced vital capacity. So that's from peak to trough. And you'll get a reading of approximately 3.4 decimeters cubed. If you want to practice, you can also practice doing the tidal volume by counting again the height of each of these. So how many squares is that? If each square is 0.1, it's roughly about 0.4 decimeters cubed. And then working out the breaths per minute. So again, make a note here, that's 2 complete breaths. Work out how many squares that takes, work out the value of the squares. In this case, each square is 1 second, and then you can multiply up till you get per 60 seconds. The last thing is oxygen consumption. So if I show it you on here, oxygen consumption, the trace goes down. All you have to do is work out by how much. So if you count the number of squares here, and you work out the value of each square, which is 1 decimeter cubed for 10 squares, so each square is 0.1 decimeters cubed, you can quickly work out that that is 0.4 decimeters cubed. Therefore, you then need to work out, if you want to work out oxygen consumption rate, you need to find out how long that took. So you start at the peak. It's always peak to peak or trough to trough, and therefore you get this correct reading. You can't do peak to trough, that upsets the reading. So basically time how long it takes from this peak to this peak. So work out 4, 8, 12, 16, 20, 24 seconds. So all you have to do then is say 0.4 decimeters cubed in 24 seconds. Scale that up, so 0.4 divided by 24 multiplied by 60 will give you the volume per minute, and that works out as 1 decimeter cubed. Okay, and that's it.